Okay, for the chemical reactions to be spontaneous, delta G is going to be negative. If the delta G is negative, the reaction is going to be spontaneous. So delta G, if it's less than 0, then we have a spontaneous reaction. Spontaneous reaction. We also were dealing with the K value, which is the equilibrium constant. What is favored for a spontaneous reaction? That means you get more product. So if you get more product, that means the value for K is greater than 1. For a non-spontaneous reaction, the value for delta G is going to be greater than 0. So basically it's going to be positive. If delta G is positive, it's going to be non-spontaneous. When it's non-spontaneous reaction, that means not much of a chemical product is going to form. Where you have the value for K, K is going to be less than 1. We could also have the process at the equilibrium. At the equilibrium, the value for delta G was 0. And the value for K would be equal to 1. So this is equilibrium. So spontaneous delta G is negative, non-spontaneous delta G is positive, delta G0 is at equilibrium. And the value for K, which represents how much product is going to form compared to the concentration of the reactant. For spontaneous, we get more product. So the value for K, which is the ratio of product over the reactant, is going to be greater than 1. For delta G positive, that means non-spontaneous, the value for K is going to be smaller. Now, how do you calculate delta G for redox reaction? To calculate the value for delta G, you need 3 variables. One is value for N. That means the number of electrons being transferred. For a reaction that, let's say you have the zinc plus Cu2 plus, that gives the zinc 2 plus copper 0, N equals 2. Because zinc is going to lose 2 electrons and copper is going to gain 2 electrons. So this N is not number of moles in this case, is number of moles of the electrons in the reaction. So we have the N, number of moles of electrons. How many electron is being transferred? We do need the value for F, which is a constant number, and that is going to be given to us. Is a constant number, is 96,500 joules per volt per mole, or 96,500 coulombs per mole. Joule per volt basically is the coulombs per mole. So we have a constant number. So N, we can find out based on the chemical reaction how many electrons being transferred. Like if you balance the equation based on half a reaction, just before adding the number of electrons that is the same on both sides. That is the number of electrons being transferred. F is a constant number, and then E cell is going to be calculated. We have 2 terms, E cell and then we have E0 cell. E0 cell is for standard condition, where concentration of the solution is going to be 1 molar, and the temperature is standard also. For E cell, that's non-standard, the concentration is not 1 molar, it's like different concentration. So as long as you understand these formulas, then we can move on for the calculations. But before we move on, let me just mention one more time what you need to calculate the delta G. You need the value for N, you have the value for F because it's constant, and you can calculate the E cell. For delta G0, this is going to be E0 at the standard, and this can be the E cell. E cell is the E0 for cathode minus the E0 for anode, and you are going to find that from the table. The values are going to be provided to you, or a table will be provided. So if it's assignment, you have the access to the table. F value is still the same for delta G, and delta G0 is going to be the same number, and N also is going to be the same, and is number of moles of electron. The other formula that we have is a delta G0 equals minus RT ln K. So RT ln K, universal gas constant, temperature in Kelvin, and the natural log of K at the equilibrium for delta G 0 to find the delta G 0, which is equal to NF cell, E0 cell. So if you rearrange this formula, you can find the E cell from this formula, RT NF ln K. So RT, you divide both sides by NF. You divide both sides by minus NF, actually, minus NF. So you have the RT NF ln K, and this is going to cancel. That equals to E0. So we have the E0 cell can be also calculated from the concentration. Concentration at the given temperature, and the R value should be given to you. Because this is constant, the temperature is the 25 degrees Celsius, which we convert to the Kelvin, 298. N is number of electrons, and value for F is constant. These three numbers for E0 is constant, so we can combine all these three, and when you are using natural log, this is going to be 0.0257, and then when you are using log, it's going to be 0.059. So this is a more simplified formula, because then you don't have to memorize and know the R value, T value, and F value. You're just in replacement of all those three, you're just knowing and memorizing one number, and it's 0.0592 over N, and N would be the number of electrons being transferred. When you have the concentration, you can calculate the E0. So basically introducing some of the formulas that could be used for calculation. If you have the K value, or if you have the concentration at equilibrium for different reactants and products, you can calculate the E0. If you have the E0, you could calculate the value for K as well. If you have balance equation, or you have the chemical equation, you can find out the value for N. Okay. For redox reaction to be spontaneous, delta G must be negative, and the K would be greater than 1. That means more product is formed. The value for E0 is going to be positive. For equilibrium, delta G would be 0, K would be 1, and E cell is going to be 0. This is at equilibrium. For non-spontaneous, delta G would be positive. The value for K is less than 1, meaning that you have less product than reactant. And the E cell value would be negative. So this is non-spontaneous reaction. If it's spontaneous, if a reaction is spontaneous, the reverse of that same reaction is going to be non-spontaneous. That's another. What's the equilibrium constant? So basically, you're trying to find the value for K for the following reaction. What do we know about the equilibrium constant? What formula we are using? We can, if we have the E0 cell, we can find the equilibrium constant because 0.059 or over n if we are using log, or for natural log would be 0.0257 ln k over n. So if you want to find the k value, we need to find the E cell and we need to find the n. We have the balance equation. We have 2 electrons gained by iron. 1 electron is lost per silver. So the value for n is going to be 2. Oxidation happens in anode, and silver in this case is being oxidized. Iron has been reduced. Since we have the E0 value for each one, for silver and for iron, we can basically say we can use the numbers for the E0 for iron and for silver. So is the cathode minus the anode. So if we have the value for iron, which is happening in the cathode, minus the value for silver, which is happening in the anode, the overall number can be calculated. If we have the value for E0, we have the value for 2, then we are using this formula in order to find the value for K. So basically E0 cell times N equals 0.0. I'm just rearranging that formula, 57 ln K. So ln K, if you divide both sides by 0.0257, 0.0257, so this is going to be cancelled. And then in order to find the value for K, you are going to take the anti-log of both sides. Ln K is going to change to K, and this side is going to be e to the power of this. We have the numerical value already calculated for E0 using the E0 for cathode and for anode. For the cell, N was 2. This is a given number, is a constant number, part of the formula, and we can have these number already replaced to find in order to find the value for K. This K value is much lower than 1. That means the reaction is non-spontaneous. And we also saw that E0 is negative for cell. So if it's negative value means it's non-spontaneous. So if you want to check your answers, then it's basically correct. Concentration. At different concentration, the E cell is going to be different. So this is at 1 molar. This is going to be at different concentration. So if you have a different concentration, you don't have the value for K. Instead you have value for Q. So at a different concentration, E0 can be different from the E cell. So this equation is known as the Nernst equation. Basically, is studying the effect of concentration at the on the E potential, cell potential. So instead of the RTLN, we can simplify it. The RTF can be simplified. For the log is this. We are using these formulas again for calculation. And when we are using it, you have to memorize it for checking. Which of the following reaction occurs spontaneous? Will this reaction happen spontaneous or is going to be non-spontaneous? So basically you have to find the value for E. And if E is greater than 0 or if E is positive, then the reaction is going to be spontaneous. How do you find the value for E? We need the E0 for the cell. So we have to find this first. Then it's going to be minus 0.257 over N ln Q. ln Q. Now, first we are going to find the value for N. These two must be known. Then we find the value for E0. The value for N can be found from the balance equation. Iron is gaining 2 electrons again, cadmium losing 2 electrons, so N is equal to. For the E0, which one is the cathode? Iron is in cathode, and then cadmium would be in anode. So we have the cathode minus the anode, and you find these numbers from the table. For iron is a minus 44, and then for cathode is going to be minus 40. Cathode minus the anode, you have the E0. E0 is negative. It's not a very large number, but it's negative. Then you find the value for E. We have the E0 already calculated. N is determined to be 2. In order to find the E, we are going to replace the concentration of product over the reactant for Q. Concentration of the product over reactant. In this case, we have 2 solids, so we don't have to be worried about concentration of these two. It's just concentration of cadmium over concentration of iron. So we have these numbers. The value for E is positive, and if the value is positive, that means the reaction is a spontaneous reaction. Okay, so even though E0 is negative, but concentration or changing concentration, it can affect this reaction. Basically, you're increasing the concentration of the reactant, and that is going to make the reaction spontaneous. So, okay, last part of this chapter is batteries, different type of batteries. Still the oxidation reduction reaction. You have cathode and you have anode. So different type of batteries. For the dry cell battery, the oxidation of the zinc is going to take place. Zinc is going to be oxidized, and manganese is going to be reduced. So manganese from MnO2 is changing to Mn2O3, and the zinc solid is changing to zinc 2+. So we have the oxidation and reduction taking place in the within the battery. This is for the dry cell. For dry cell, we are dealing with zinc and manganese. For mercury battery, we are going to deal with the zinc and mercury. Zinc is being oxidized. Okay, zinc from 0 is going to zinc 2+, and here is 0. Losing 2 electrons, zinc is being oxidized, and mercury is being reduced. So mercury is going from 2+ to 0. Mercury is being reduced. This is the overall reaction. Zinc, mercury, plus the mercury oxide is changing to zinc oxide and mercury liquid. So this is the mercury batteries. For lead storage battery, both anode and cathode, reaction anode and cathode is going to be based on the lead. So, but in anode, lead element is going to be oxidized to lead 2+ here. and with the sulfate combines, and it's going to give you release 2 electrons. It would change to lead sulfate. For cathode, we have the lead oxide. This is a 4 plus, because each oxygen is 2 minus. We have 2 oxygen is 4 minus, so lead would be 4 plus, changing to 2 plus. Why 2 plus? Because SO4 is a 2 minus. So oxidation number has decreased, so this is reduction taking place here. So lead oxide being reduced and lead metal is being oxidized. This is for the lead storage batteries. Then we have the solid state lithium batteries. We have batteries for fuel cells, and the fuel cells, hydrogen is being oxidized and oxygen has been reduced. Hydrogen is losing electron, changing to water in a basic solution, and oxygen has gained electron, changed to hydroxide. So hydrogen being oxidized and oxygen being reduced in the fuel cell. Corrosion, what is corrosion? Basically, oxidation of the metal is called corrosion, and it's going to lose the metal when it's oxidized. It's going to lose its strength, so it's being corroded, and it's deteriorated, like iron that is hard metal. After it changes to iron oxide is like a brown powder. So it's oxidation reduction reaction, because metal in presence of oxygen is going to be oxidized. The iron changing from iron solid would change to iron 2 plus or iron 3 plus. Then you have oxidation taking place and oxygen being reduced. So oxygen gains the electron from the iron and it changes to water. So when you see corrosion, basically is oxidation reduction type reaction. Metal is being oxidized and oxygen has been reduced. Protection, cathodic protection, that means we have to connect this metal piece in order not for this one not to be rusted. We can connect it to more reactive metal. Like if you have a piece of magnesium here, magnesium is going to oxidize before iron oxidizes. So these electrons are coming from magnesium to satisfy the oxygen that is here to be reduced. So oxygen that is looking for electron is going to gain the electron from magnesium, not from iron. And as a result, the iron is going to be protected. So in order to protect the iron, like inside the oil, you have to connect it into for the storage. As a storage tank, you have to connect it to more metallic element that is more reactive. But the electrolysis is a non-spontaneous chemical reaction. Basically, you are going to provide electricity for the reaction to take place. So in electrolysis of water, hydrogen gas and oxygen gas is going to be produced. So what is happening? Oxidation would happen for oxygen. Oxygen would be oxidized, losing electron and changing to O2 gas, and then hydrogen is being reduced. H plus would change to H2 gas, and it is reduced. So oxidation reduction is taking place in electrolysis reaction, but the energy has been consumed. Electrical energy has been consumed because this reaction is not a spontaneous reaction. But still, reduction takes place in cathode and oxidation takes place in anode. In the electrolysis or electroplating, the mass is going to increase. Mass of the substance or the element that is being reduced is going to increase. And you can actually find out how much electricity is needed for 1 mole of the compound to be deposited or to be formed or change mass. So for every mole of electron, you need 96,500 coulombs. This is the Faraday constant. So you need this much of the electricity to generate or to provide 1 mole of electrons. So number of moles of electrons, moles of the substance being reduced or oxidized, that is coming from number of electrons has been provided. And then if you find the number of moles of the substance being reduced or oxidized, you can then change that to the gram using molecular mass. How much calcium will be produced in an electrolytic cell of calcium chloride in current 0.452 amps is passed through the cell for 1.5 hours. So calcium in this case needs to be reduced. So calcium ion is changing to calcium metal, and chloride is changing to chlorine gas. How many electrons do we need? 2 electrons for the calcium ion to change to calcium. So we need the 2 moles of electrons. So if you provide 2 moles of electrons, then 1 mole of calcium will be produced. If we will provide 1 mole of electron, then half a mole of calcium would be produced. So first we need to find out how many moles of electron has been used or passed or being passed through the cell. How many moles of electron? How many moles of electron? We can calculate that based on the amps that we have. The amps or coulombs per second is the same thing. So we have 0.452 coulombs per second for how many seconds? 1.5 hours. Each hour is 3,600 seconds. So we multiply that by 3,600 to get into seconds. So this is the total number of coulombs that we are getting. So if we have the coulombs, then we want to change that to number of moles of electron. Every mole of electron requires 96,500 coulombs. This is per mole of electron. So if we have the mole of electrons, then how many electrons do we need? How many moles of electrons do we need? 2 moles of electron per mole of calcium. Then we multiply by 1 mole of calcium over 2 moles of electrons. So we get the moles of calcium. If you multiply this by 40 grams per mole of calcium, we get the grams of calcium that is being produced, or the gain, the mass gain, if we pass this amount of electricity for 1.5 hours. So basically, you are going to convert the current, the electricity, to number of moles of electrons. The ratio that you are using, it's the 1 mole of electron over 96,500 coulombs. Okay, that's the last slide. I'm going to stop the recording here and